Particle swarm optimization is a population-based optimization algorithm inspired by the collective behavior of natural systems such as bird flocks and fish schools. It belongs to the family of swarm intelligence methods and is widely used for solving continuous and nonlinear optimization problems. The main idea behind the method is that a group of simple agents can collectively discover optimal solutions by sharing information and adapting their movement through the search space. In particle swarm optimization, a set of candidate solutions called particles moves through a multidimensional search space. Each particle represents a possible solution to the optimization problem and has a position and velocity. The position encodes the current solution, while the velocity determines how the particle moves in the next iteration. Unlike evolutionary algorithms that rely on crossover and mutation operators, PSO uses cooperative behavior and memory-driven dynamics. Each particle keeps track of two important pieces of information. The first is its own best position found so far, which is often called personal best. The second is the best position found by the entire swarm, or sometimes by a local neighborhood, which is called global best or neighborhood best. These two attractors guide the particle's movement and create a balance between exploration and exploitation. The movement of particles is governed by a simple mathematical update rule. At every iteration, the velocity of a particle is adjusted based on three components. The first is inertia, which keeps the particle moving in the same direction as before. This encourages exploration and prevents premature convergence. The second is the cognitive component, which pulls the particle back toward its own best solution. The third is the social component, which pulls the particle toward the best solution discovered by the swarm. By combining these influences, the particle dynamically navigates the search space. One of the strengths of particle swarm optimization is its simplicity. The algorithm has relatively few parameters compared to other metaheuristic methods. Common parameters include inertia, weight, cognitive coefficient, and social coefficient. Despite its simple formulation, PSO can solve complex optimization problems efficiently and often converges quickly. The absence of complicated genetic operators makes it easy to implement and adapt. The balance between exploration and exploitation is crucial for the success of PSO. Exploration allows the swarm to search new regions of the solution space and avoid local optima. Exploitation focuses on refining promising solutions to achieve higher accuracy. Adjusting parameters such as inertia weight over time can improve this balance. For example, a high inertia weight early in the process promotes exploration, while a lower value later encourages convergence. There are many variations of particle swarm optimization developed to improve performance in different scenarios. Some versions introduce adaptive parameters that change during the optimization process. Others use hybrid strategies combining PSO with local search or evolutionary methods. Binary PSO adapts the algorithm for discrete problems, while multi-objective PSO extends it to problems with multiple conflicting objectives. Particle swarm optimization has been applied across a wide range of fields. In engineering, it is used for design, optimization, control systems, and signal processing. In machine learning, it helps tune hyperparameters, select features, and train neural networks. In operations research, PSO is used for scheduling, routing, and resource allocation. Its ability to handle nonlinear and non-differentiable problems makes it especially valuable in real-world applications where traditional gradient-based methods struggle. Another important aspect of PSO is its scalability and flexibility. The algorithm can be parallelized easily because particles operate semi-independently while sharing minimal information. This makes it suitable for high-dimensional problems and large-scale optimization tasks. Additionally, PSO does not require gradient information, which allows it to work on black box functions where the internal structure of the objective function is unknown. Despite its advantages, particle swarm optimization has some limitations. It may suffer from premature convergence, especially in complex multimodal landscapes. If the swarm converges too quickly, diversity is lost and the algorithm may settle in suboptimal regions. Researchers address this issue by introducing mechanisms such as random reinitialization, neighborhood topologies, or diversity-preserving strategies. Evolvable hardware is a field at the intersection of evolutionary computation, digital design, and adaptive systems. It refers to hardware systems that can automatically modify their structure and behavior through evolutionary algorithms in order to achieve specific goals or adapt to changing environments. Instead of being manually designed and fixed, the hardware architecture itself evolves over time. The concept of evolvable hardware emerged from combining ideas in genetic algorithms and reconfigurable devices such as field programmable gate arrays. A foundational contribution to the theory of evolutionary computation was made by John Holland, whose work on genetic algorithms laid the groundwork for applying evolution to engineering design. Later, researchers explored how these evolutionary principles could directly influence physical hardware configurations. Evolvable hardware can be divided into two main categories: intrinsic and extrinsic evolution. In extrinsic evolution, candidate hardware designs are evaluated in a simulated environment. The evolutionary algorithm runs on a computer, generates different hardware configurations, and tests them through simulation before implementing the best solution on real hardware. This approach is safer and faster during development because it avoids physical risks in hardware wear. In intrinsic evolution, the evolutionary process occurs directly on the physical device. The hardware reconfigures itself in real time, and the evaluation of each candidate solution happens in the real environment. This approach is more powerful in certain contexts because it captures real-world noise, timing issues, and environmental effects that simulations might not model accurately. However, it requires robust hardware platforms capable of rapid reconfiguration. A key enabling technology for evolvable hardware is the reconfigurable chip, especially field programmable gate arrays produced by companies such as Xilinx and Intel. These devices allow logic circuits to be reprogrammed after manufacturing. Instead of fixed wiring, their internal connections can be modified dynamically, making them ideal for evolutionary adaptation. In a typical evolvable hardware system, a population of candidate circuit configurations is encoded as chromosomes. Each chromosome represents parameters such as logic gate connections, routing paths, or functional blocks. The evolutionary algorithm evaluates each configuration using a fitness function that measures performance according to desired criteria such as speed, accuracy, power consumption, or fault tolerance. Through selection, mutation, and sometimes recombination, better configurations are gradually discovered. One important application of evolvable hardware is fault-tolerant systems. In harsh environments such as space missions or nuclear facilities, hardware components may degrade or fail. Instead of relying only on redundancy, an evolvable system can reconfigure itself to bypass damaged components and restore functionality. This makes it highly attractive for autonomous systems operating far from human supervision. Another application is adaptive signal processing. Communication systems can use evolvable circuits to adjust filters, controllers, or modulation schemes in response to changing noise conditions. Robotics also benefits from hardware that can adapt to new tasks or environmental changes without requiring complete redesign. In these cases, evolution enables hardware-level learning rather than relying solely on software updates. Evolvable hardware also plays a role in unconventional computing. Researchers explore evolving analog circuits, mixed signal systems, and even nanoscale devices. In some experiments, evolution has produced circuit designs that human engineers would not intuitively create, demonstrating the creative potential of evolutionary search in hardware design spaces that are too large for manual exploration. Despite its promise, evolvable hardware faces challenges. The search space of possible hardware configurations is extremely large, making convergence difficult. Real-time intrinsic evolution can be slow if each candidate must be physically tested. There are also concerns about reliability, verification, and safety when hardware autonomously modifies itself. Ensuring predictable behavior in safety-critical applications remains an active research area. To address these issues, hybrid methods are often used. Designers may combine evolutionary algorithms with local search, machine learning, or constraint-based design techniques. Partial reconfiguration is frequently employed so that only certain sections of hardware evolve while core control structures remain stable. This balances adaptability with reliability. In summary, evolvable hardware represents a shift from static circuit design to adaptive, self-modifying electronic systems. By integrating evolutionary algorithms with reconfigurable hardware platforms,